So I've been fortunate. So I would now start presenting. Right. So my topic today is going to be on and around 800 volts architecture, and trying to talk about how it is contributing towards faster EV adoption and what are the key benefits coming through it. I plan to also touch across what are the upcoming changes across the leading edge OEMs on new component designs, new architectural approaches, and how efficiency, cost, range, charging are all intertwined with each other, and how cost heavily affects design, as well as how design equally affects cost in terms of the more higher voltage and higher efficiency we reach towards, the better cost, therefore better charging, therefore better adoption. So that will be part one. Then I'll be also touching across some of the, I'll take an example across some of the new take an approach of integrating their componentry on the vehicle, therefore trying to award more space to their consumers, trying to give more and more features by making their powertrain architectures as well as overall vehicle architectures as compact as they can. And I'll try to explain that through a case study of integration of onboard charger, DC-DC, and BMS, the cost improvements of that, and what which most of the OEMs are nowadays exploring. And when I say most of the OEMs, these are premier automotive companies like BMW, Tesla, Daimler. So as I said, this is the agenda that I have for today. So initially I'll be talking about what are the charging system requirements that the consumer today expects for adopting EVs. So I'll touch upon what is the access and duration that surveys indicate, what evidence do we get from some of the surveys that we have done, what are the typical challenges across infrastructure, and actually also spend some time on what is the actual utilization of the charging systems, therefore trying to give an insight of how the consumer perceives usage of an electric vehicle. And these are typically centered around Western geographies. I will also try and touch upon the shift in charging towards 800 volts and how it affects the range, meeting the targets for the range. Then in the second section of today's talk, I'll try and talk about how the architectures of 2025 on a battery electric vehicle look like, with the new advanced requirements of vehicle to grid coming in, trying to see load shedding, and trying to have vehicle as an energy source for powering your own house. I'll also try and touch upon what is today's competitor roadmap looking like for 2025, which basically touches upon what different OEMs are doing. And towards the end of that section, I'll try and talk about what would be the right time to move to 800 volts. And as I said, I'll try and take a case study and explain the industry trend towards integrating charger and a DC-DC and why that is the case. And I'll also explain some of the other work that's going on in machine design and inverters, and how integration is helping the cost and packaging aspects of the vehicle. And then we will go across some of the how future of these integrated components looks like, how they will become more and more component. And towards the end, I will try and touch upon even after 2025, how do things keep getting more compact and better, which is when silicon carbide starts becoming mainstream as a channel material replacing silicon. So that would be the topic that I have, set of topics that I have. So we've done, as part of our strategy, we've been involved in several large surveys as participants to it every time. And we've got basically some of the metrics here have been looking at what is a typical time a consumer looks for towards charging. So as I said, these are centered around Western geography. So for a consumer who's buying a premium car, he wants almost 80% of his range to be, or at least a manageable range to be updated on his vehicle within 15 minutes of time. That is the biggest selling point. Up to 30 minutes, people are okay. They would still be considering buying a vehicle, although they may or may not buy it. But crossing an 18-minute to 15-minute barrier definitely gets them towards buying a vehicle. And anything about 30 minutes is almost unacceptable. Now, we'll also touch upon how much people do really use, but this is clearly talking around what the consumer thinks. So that's a key element in defining and designing architecture, and that's where a standard OEM, that's how they start creating requirements. So basically, you go through surveys, you get an understanding of what the consumer wants, and then that gets decomposed into basically strategic requirements, which are then converted into vehicle requirements. Those vehicle requirements get further decomposed into attribute targets, and those attribute targets are then taken up by us as component designers towards defining what the boundary conditions of the component should be. So in that process, as you can see, the topmost priority goes to what the consumer wants, what the customer wants, and we are designing towards that. So with things such as the purchase price, the driving range, the brand of the vehicle, reliability, performance and handling, all those indicators are improving significantly day by day. As volume increases, prices are naturally going down. The problem that still continues to aggravate is the time to charge the vehicle. And that's why I wanted to focus today's discussion around some of that topic that continues to be and will continue to be a challenging topic towards adoption. So some of the evidence from early surveys that BMW, Nissan, Porsche, Audi have all come together to do is around where and how much charging people do. So typically in a household setting or a workplace setting, household as in when you buy a car, you're naturally given an option to install a charger at your home. So or if you're working, you typically go in and you park your vehicle and plug it into the car. It's nowadays a very common scene in most of the Western geographies. So those typically range between 3 to 22 kilowatt. So that's AC charging. So it can either be a slow AC charge, it can be a fast AC charge. Then there is DC charging as well, which typically you won't find in a household setting, but it would be in your workplace or places where you go for spending more time, like shopping malls and hotels and any other hospitality areas, or consumers in urban fleets such as Uber and or taxi fleets. So those are typically ranging between 20 to 25 kilowatt, and the typical charging time there is 1 to 3 hours. And then there is fast charging stations, which are basically centered around retail parks, grocery stores, smaller restaurants, etc. Those will charge about 80% of your vehicle in 90 minutes. And then there is high cost, very high power, very expensive to maintain, starting from 150 all the way to 350 kilowatt, very high DC power, which basically will charge your vehicle under 15 minutes. Now, all these surveys indicate that almost, or in about 99% use cases, 85% of the customers will be charging their vehicle primarily in the first category, which is in between 3 to 22 kilowatts. That has been the evidence from these surveys. So when we design for a vehicle, why this is important? This is important because we will have to also try and understand that if we try and design the power electronics to meet the DC high power, we'll end up making the vehicle much clear, therefore driving the customer away from it. I think one has to be very careful of how this infrastructure is evolving, and therefore design our componentry according to that. So currently, the focus still remains on AC charging, which in Western world we call it as AC slow charging, and the DC aspect of charging still continues to be an offering, but it's offered more as an option fit. Now I'll try and tell what option fit is. So when vehicles are designed or architectures are designed, there are cost models defined, and usually you try and design for the lowest cost model. In the olden days, vehicles used to be designed for medium tire cost models. Every company has different cost model tires. It's a higher cost, medium cost, and lower cost. What that means is, for example, when you go to buy a car, you choose a variant. You want the variant with highest features, variant with medium features, or variant with no features, like no power windows and etc. So in the olden days, people used to design for the medium tire, and then everything below that would give more profit to the OEM, and everything above that would still give more profit to the OEM. With competition growing every day, that has now changed to the lower tires. So everybody has started designing vehicles for the base architecture, and everything above that is a feature addition. And if not designed properly, it can quickly become a loss-making vehicle line for you, and not remain anymore a profit generating asset. Which is why nowadays we see a lot of conventional OEMs struggling to try and meet the demands of the consumers around prices, and newcomers like Tesla growing really fast and reaching valuations like never before, because they've been setting the trend of designing towards the lowest spec. So that's the significance of this slide. So basically, when we design components, we design towards the lowest spec, which is maximum use case as well, which is AC charging, and everything above that is provided as an option, which is if for example, if a consumer goes to buy a car, he will get a base car with conforms to AC and DC up to 20 kilowatts, but anything above that he would want to buy it as an extra feature, and that would be configured for him, just as you get a new paint or you design the paint scheme for your vehicle and you get the vehicle customized for that. So that's basically centered around how the customer is using is going to be offered vehicles in future, and at the same time how the utilization of charging is happening right now. These are some more realistic figures as well, which is showing a typical utilization as a percentage of how these charging stations, how these charging systems are being used. So as you can see clearly, anything above 50 kilowatts, which typically nowadays, if you go into Western countries, you'll see it on the motorway exits, and you'll see those big Tesla chargers. But even within Tesla users, those and across all OEMs, the utilization of that continues to be under 0.3% consolidated. And anything above DC is all less than 10%. Most use cases, 93% use cases, are all AC charging, which is what people have accessible at home. So moving forward, now, how do we improve charging? Basically, with 400 volts, the limit of charging. So the unit typically, nowadays, the unit typically used is how many kilowatt hours can I charge in a minute? So with 400 volts, the boundary is getting reached at about 2.5 to 2.7 kilowatt hours per minute. And that's basically looking at about 32 amperes of current on your AC line. With 800 volts, that mark goes significantly higher to about 4.5 kilowatt hours a minute, which is almost twice of that. So you can achieve almost twice the amount of charging with the same infrastructure, but at a higher voltage. So even with AC charging, but if it is at 800, you can be able to, you would be able to achieve a much higher, I would say, performance on your charging system. So below are some of the estimates and the actual numbers of some of the OEMs. So as one can see, standard, an average OEM as of 2021 will be centered around 2.3, 2.1 to 2.3 kilowatt hour per minute. Tesla is already ahead of that with 2.5 kilowatt hour a minute. And the industry leader at present, although I think this slide is a bit outdated now, the industry leader is now Lucid Air. But when the slide was made, the industry leader was Porsche Taycan at 4.6 kilowatt hours a minute. Lucid Air is currently the market's leading charging system adopted on a vehicle, which is about 5.3 kilowatt hours a minute. I think if you look at it, it's a common trend. The German OEMs are still lagging behind. I mean, the conventional large size German OEM, Porsche is a German OEM, but it's more performance driven. So the likes of Mercedes, Audi, or even ourselves, we are much behind the typical BEV threshold. So the point is, as the efficiency of the vehicle improves and as the charging system improves, we would be able to offer customer a better charging performance at the same cost and with the same infrastructure. So the idea is to try and hit a 15-minute target as fast as we can in order to continue our, I think, foray into electric vehicles going forward. That's the target we work with. So what are the other advantages that we have with increasing efficiency? So today, when a typical consumer charges the vehicle, the biggest problem with battery electric vehicles, when you charge the vehicles or you leave the cars on standby, is not actually a problem with the battery. It's actually with the high voltage battery. It's actually your low voltage battery goes flat. And that has been a major issue across all OEMs. Take it Tesla, take it Jaguar, take it Land Rover, or even a Volvo or any other vehicle, even if it's known for reliability. The reason for that is power electronics requires significant cooling to keep it steady. Charging will increase temperature. It activates the fans. And if a vehicle in a standby has cooling fans going on, it drives the battery almost to a level of flattened low voltage battery. And that has been actually a big warranty increase on vehicles. And the major reason for that is power electronic switching increases temperature at the junction, causing fans to go on. And that has been an issue that the cooling system has not been able to cope up with it, because even to activate a cooling system, you need to, most of the premium architectures will be on HVAC enabled water glycol cooling system. So that will engage your compressor. Therefore, it will have a high voltage battery also active just to have your cooling system on. So with increasing efficiency, we would be able to reduce the burden on cooling system. And if we can achieve that, that helps us to therefore save the overall warranty spend on the vehicle. So that is why the efficiency of the onboard charger, which is basically the element that takes in energy from the charging station, is significantly important in trying to address the challenges on warranty that one faces due to increased burden on cooling system. So that is a significant advantage one would achieve with increasing efficiency of the onboard charging. It's a simple logic. As the DC voltage increases, your current will go down. And as we all know, basically heat losses are I square R losses, impedance losses in your wire. So it is a loss coming through the resistive element, through the inductive element of the wire, and at the same time your capacity. The other issue is that with increasing inductance, you also have an issue of transient voltage, which is giving us a lot of problems in field as well as all OEMs, causing componentry to go out of bus because of high current inrushes. So with voltages going higher and higher, one, we will be able to give more performance, but at the same time, the current reduces, therefore reducing our risk towards effects like transit voltage issues on the vehicle, and therefore warranty spend on components, and also recalls around that. Moving to the next section, so I tried to talk about what are the typical expectations of the consumer on charging time, what evidence do we get, what is the utilization, and how does shifting to 800 volt offer better Now, I'll talk about the 800 volt system. I'll first talk about how the platform, what a 20, then I'll talk about what a 2025, then I'll explain the difference between a battery electric vehicle and a plug-in hybrid, because I think battery electric vehicle is still not mainstream across a consumer's purchase interest. They would typically go for a plug-in hybrid even today. And there's a difference to how both are progressing. One is moving towards a higher efficiency, higher performance, and the second is more moving towards cost focused, trying to reduce costs as much as it can so that they can package more and more of range and features along with IC engine into the vehicle. And I mean, it's a simple logic there again, because with a plug-in hybrid, you have your electric traction system and your ICE traction system, and you want to offer both at almost the similar cost of a diesel. So you will have to despec both of them. So you won't be able to really optimize both of it to um, premium performance on either of them. Then I'll talk about vehicle to grid and how it's posing challenges and for design and what it means in terms of costs. And I think that will also, these three topics will also try and give some direction to why I've chosen the example of charger later on, which is the onboard charger and DC-DC. And I'll then talk about the competitor roadmap, which is basically talking about how different OEMs are approaching this topic and what are the typical timeframes, which models are coming across on these architectures. And towards the end, I'll quickly show through a drawing what's the right time to move to 800 volts. Um, on your left, as you can see, is a typical 400 volt BEV platform around 2018-19. And you would have seen pictures like this all across. Different OEMs are trying to publicize. What you see on your right is what Hyundai has revealed on 2nd of December this year, which is their new GMP platform, a modular BEV focused platform, which they are heavily integrating components. So I'll try and touch on that topic now. So in the olden days, sorry to say olden, but when a 2018-19 platform is released, work starts around 2014-15. That's why. So the components are all discrete. So the battery, yes, the battery was the architecture is called as a skateboard architecture, which is that the vehicle is designed around the battery. So battery takes the center stage. As you can see, the battery shape is very particularly designed for meeting the structure has been designed to meet the battery's shape on your left hand side. And then you have your components, which are all distinct. So you have a different junction box in which you get your DC link from the battery. That has a connection to your onboard charger. You have a separate DC-DC system. Your contactors are sitting in a power distribution unit, and then you would have your inverters and motors both sitting on top of each other, but still distinct. Meaning, in industrialization, you would have a motor coming and sitting on your vehicle, and then you will place the inverter, and then you will take the 3 AC cables and connect them. So basically, your as an OEM, it would be the OEM which would be integrating all of this on the vehicle when they're assembling the vehicle. And that leads to problems. That leads to many problems, especially with more wires. One is more cost, but the other significant problem is when you try and connect them, there are problems that come with connectors. There are crimping problems. There are problems with copper loss. There are problems with quality of copper. And then the worst of everybody and the nightmare for any OEM is the contactors. Those give the biggest problem, and those are very difficult to detect. A slight amount of dust will cause a contactor weld, and that's it. Then you've got a contactor last event, probably so bad that you have to just go and replace the contactor. And just to explain the impact of it, every time you have a contactor replaced event, it costs the company at least $7 to $8, including on an average, and that includes part cost, a person's cost to go and get it changed, and at a large scale. These are average figures, but the reason, although $7 on a $80,000 car may look small, but just to explain how every dollar counts, um, when we look at $1 and about 500,000 vehicles, it suddenly points to 500,000. And typically, any OEM in premium category BEV, which is trying to sell these cars, its profit margins are less than 5% of the selling price. And that margin also needs to account for marketing costs and other areas. So the actual part cost that you're playing around with is less than $100. So now that I try to put that in perspective, $7 and $100 is quite a big figure to try and aim for or achieve, reduce. So on the right hand side, if you can see, you no more see those inverter or the motor separate. You just see a single DC cable going into the battery. The battery is more flat. It is more it is more of sitting into the structure rather than the structure sitting around the battery. And then the inverter and the motor are all assembled in a single housing. And furthermore, in the olden days, the inverter was a planar geometry which used to sit on top of the inverter. And now, with better understanding of the power electronics, inverter itself is getting changed into only the control boards going above the motor, but the power boards actually sitting right next to your rotor. Therefore, you eliminate those 3 AC cables and rather just have 3 bus bars, which is actually a great thing, because then bus bars are more robust than a cable. You no more have to worry about crimping, and your power boards are right next to your rotor, which is best because you have no longer losses that you would have in cables. So you improve efficiency there. Then the charging system is now completely integrated. People have started, Hyundai has now integrated the charger, DC-DC, and their BMS. So the battery is literally just bank of cells and wires coming out to the integrated charger, and the battery management is actually sitting inside the charger. And we'll talk about that later. And with the charger is actually equipped for bi-directional charging, which means you can use the charger, you connect the charging gun to your vehicle, charge the car, but at the same time, the same charging gun will also take power from your vehicle and power your home. For example, if you have a power cut, you can take power from your vehicle. Or if you are doing load shedding, you could use your vehicle as an energy storage and use the energy during night time to optimize pricing and all of those. So moving forward, Lucid Air has been, I mean, this is the vehicle that has been in talks everywhere, and it's been an innovation, a proper case of innovation across all components. And it's just been like before Hyundai came with the cost optimized future platform, Lucid is more of a premium advanced platform. It sits on a 900 volt architecture. It awards about 1000 horsepower of traction power on our vehicles. And I mean, just to give a typical comparison, a standard Honda vehicle is about 120, 130 horsepower. So we're now sitting with 1000 horsepower with an electric vehicle sitting at 900 volts. It's available at the same cost of a Tesla, and they have integrated exactly like what Hyundai has also done, which is the batteries part of the structure. You no longer see inverters here because they are now integrated as part of your machine. Those are now called as compact drive units. The planar architecture is taken off and only the control board sits outside. The power board is actually integrated in the motor housing itself. So you have your power board, you have your rotor, and you have your transmission on the other side, all sit in one axis rather than your inverter sitting on top of your rotor. And similarly, your charging system is completely packaged into one complex structure, having your DC-DC, your onboard charger, and your battery management system all combined together, which therefore also helps these OEMs, because then they can stop worrying about assembling the battery packs and contract them to the partners that they just want the batteries to be assembled. So their contract would be, okay, we need so many modules packaged in so many battery packs and so many wires out of it. Helps them in warranty as well. And the only connection to their charging system would be through the wires, which is used by the BMS to monitor the cells. And that significantly improves, I think, the risk and the liability an OEM would have against having control boards integrated in different components. More computers in the car, more head communicating between each other. So the other ideology that I missed earlier is try and make as many components as dumb as you can, and try to have just one smart brain in the car, which is, or maybe 2 to 3 smart brains which are controlling the whole vehicle. And that's the key to trying to reduce warranty and other failures across products. So Lucid has been currently leading in charging. They're the fastest charging system ever offered on a vehicle. And because of these innovations on packaging and therefore better power electronics, I think, capabilities that they've achieved, they also offer more package space on the vehicle. So they have the largest boot space. Their cabin is the largest across SUVs and sedans. So I mean, if you all get a chance, have a look at Lucid's promotion videos. That really, I think, state of the art for any power electronics engineers to look at. Now, what would a 2025 electric vehicle look like? By 2025, we anticipate we would have to offer both 400 volt and 800 volt capability on the battery pack, which means that you would have a mix of charging, which is both 400 and 800 volts. What that means for the vehicle is, and this is how I think it will also give a good idea of how we, I think, have to design our componentry to the attributes. So the consumers would be in a mix of 400 and 800 volt architectures and infrastructures available to them, which means our contactors would have to be switching between creating a 400 volt configuration on the battery and an 800 volt configuration on the battery. And based on the infrastructure and understanding the infrastructure, our communication has to get the contactors to align and realign and allow the charging to happen to meet to try and give consumer as much as benefit as they can with the infrastructure that they have. So as you can see, because the infrastructure is complex and difficult to raise, it is also increasing complexity on an OEM to design the component to meet both 400 and 800 volt system. With chargers, we still see, as I said earlier, AC charging is dominant, and even with DC, most utilization is under 20 kilowatts. So 11 kilowatt DC-DC is the standard being used and will continue to be standard. Everything above that will be an option fit. I explained option fit earlier. The drive units will be high efficiency. So you'd still have 800, but some platforms will still have old 400 volt drive systems, and typically powers will range between 100 to 250 kilowatts for a standard OEM, and performance will obviously be a much higher. As I explained earlier, the inverters will start getting more integrated directly into the machines at the rotor end, and also will be more of like sitting in a single axis rather than having different geometries and being assembled together. It would be rather sitting in the minimum Z direction and also minimum X and Y direction. The motor technology still will be mixed. We still see a combination of permanent magnet synchronous machine as well as asynchronous induction machines being used across 400 and 800, and that's primarily because one machine, I mean, for example, Tesla uses two different machines. They use a induction machine to give higher torque, and then they will, I mean, it's configured for a higher torque. Actually, an induction machine has a lower torque, but they use that because of efficiency reason, and then the permanent machine is used for faster speeds, and because it will have more efficiency at higher speeds. And as I said earlier, 22 kilowatt will be option, but more importantly, all platforms will need to start supporting vehicle to grid. And I'll explain that in the how it affects the power electronics later on. The cooling systems, the air conditioning will all move to 800, but there will still be legacy 400. And I think this will add to complexity, because it's also possible that a vehicle could have an 800 volt inverter, 800 volt, inverter machine, and an 800 volt charging system, 800 volt battery, but a 800 volt compressor may not be available. So you'll have to also have to support a 400 volt compressor in your vehicle. So that continues to be a challenge, and I think we have to design our components to that. So all of this adds to cost, because now we have to design a high voltage to high voltage DC-DC, which steps down from 800 to 400 to meet the demand of your 400 volt consumers on an 800 volt architecture, and also your 12 volt system. And I think with more and more electrical features, and when I say electrical, those are the 12 volt features coming on the car, like autonomous driving, your more screens on the car, I would say more features centered around consumer, I would say enhancing experience of consumers, that increases load on the vehicle. So every time an ADAS engages brake by wire or any other element, that significantly takes power of your LV bus. That takes about 1 to 2 kilowatts of power. So in the olden days, your 12 volt architectures would be designed to handle 2 kilowatts. Now that has gone to 4 kilowatts. So we have to cater to those requirements. And yes, you would have a combination of 400 and 800 volt wiring harnesses on your vehicle, and you need to have your charge inlets also supporting both AC and DC. So that protocol still will continue to evolve. So we may still have to worry about having two inlets on the vehicle as well. So that's what a typical BEV powertrain looks like. As you can see, at a summary level, it will be a complicated system, because it will still be in a transition towards 800, but still not moved away from 400. Therefore, it will be having to offer both capabilities, 800 volt and 400 volt, both for charging and for consumption. Now we'll look at the PHEV vehicle, which is a plug-in hybrid. So this is going to be slightly different. So this industry estimates that will be still at 400 volts. The charging system still will remain 11 kilowatts as per the use cases. What rating of the machines will go down to meet about 60 to 80 kilowatts at 400, and that's primarily because of the PHEVs will be used only up to about 40 miles per hour speed limits, and then the ICE engine will kick in, and that's primarily because of cost reasons. Because the higher the kilowatt, the higher we'll have to spec our switching MOSFETs, and therefore the power boards will start getting costlier. It's a very linear relation of dollar per kilowatt. As your kilowatt goes up, your dollars will go up on the component. So I think there will be cost cutting starting to come there on the kilowatt rating of your machine, and with the new work happening with suppliers like GKN and ZF, the transmission on the IC engine itself is having this 60 kilowatt machine being packaged into it. So and the benefit of that is at cold start, you can start with your machine. Today, you still need to rely on a starter motor in minus 15 degrees Celsius. You can't use your machine because it is belt driven. So if you have your machine integrated in the transmission, you don't need a belt. Therefore, you're more able to get delete your starter motor and other components which take lot of current, lot of wiring system burden of your car. So again, everything, as you can see, I'm trying to also place my comments centered around cost. So everything on plug-in hybrids is about cost, because you have to package an engine and a machine and a battery pack all at the price of a diesel vehicle. The engines will also start getting despecced. So in a typical setting where you would buy a 6-cylinder engine earlier, you will start buying only a 4-cylinder engine. So this continues. This trend will continue. Um, then the charge inlets would be not two; it would be just one, and 800-volt update. We still don't see that happening on this until 2028, 2027, 28. So that's how a plug-in hybrid platform will look like. Now, V2X capability, I think that's going to be defining element of for 2025, like what it looks like. So it's going to be very natural to start seeing vehicle giving power back into your home, and for example, your vehicle through your solar panels during the day, and then use that energy during the night for consumption if required. And then different V2X models, such as vehicle to vehicle in emergency situations. If a vehicle is sitting at roadside flat, battery goes flat because our range has exited and fault has come and caused a massive degrade on the vehicle, and you call a roadside assist rather than trying to carry diesel chargers, which is what happens today. When you see those trolls in newspapers where people show diesel chargers being used to charge electric buses, it will start moving towards vehicle to vehicle. So you would take a DC gun from your from, let's say, vehicle 1 and connect it to vehicle 2, and then charge to give that emergency range to go to the nearest charging station. It's vehicle to home or building, that's V2H. Your vehicle to load, for example, if you need to, let's say, have a lawnmower in your garden, and you have a car parked in your, let's say, garage next to your garden, you can plug in your lawnmower into the charging station and take power out of your vehicle. And vehicle to grid, obviously, because that's when I think consumers will want most money out from their vehicle, which is they use their vehicle battery itself as an energy storage. So the Tesla power wall that we all see will start disappearing. It will rather be part of your car now. So you use the batteries of your car to give energy back into the grid. And it's difficult to imagine every time, but I think if one spends some time, weekends, if nobody's driving, and you charge the vehicle during the day and feed the power back into the grid at evening times when the peaks are high, I think that will start adding more value to the customer. So moving forward, so this is what a competitor roadmap looks like, and I want to spend some time around this. So just to explain, on the left hand side, the categories are in an ascending order from below for SUV and for a sedan. So when I say SUV2, SUV3, SUV4, they start increasing in their size. So SUV2 is your entry level vehicle. SUV3 is typically your mid-size SUVs, and these are all premium. SUV4 is today's big SUVs, and SUV5 is a new incoming category, which is like premium size SUVs, which hasn't been offering in diesel or petrol segment so far. So this is something that electrification is unlocking, which is more grand vehicles. And same goes with the sedans as well. Sedan 3 is your most entry level sedans, like for example BMW 3 Series and Mercedes C-Class. Sedan 4 is your standard executive class sedans, and sedan 5 are your high premium category sedans, like a S-Class kind of sedan. So just to explain the color scheme, the orange colors are where one sees 800 volts starting to come, and this is basically, and the numbers in brackets show the years in which these vehicles are coming out. So as you can see, pretty much most OEMs are having at least one of their platforms coming on 800 volts architecture next year. So Daimler has been, I think Daimler and BMW have started. I mean, BMW has been a leader on 400-volt architecture among the German OEMs. So as you can see on your right hand side, they have almost their entire platform electrified already, which is they recently launched their iX, which is basically an X5's version of electric vehicle, which comes out in January or calendar year January 21. So and then they have all their other sedans also electrified already, and they have already started transition to 800 volts, whereas Daimler, which started slightly later than BMW, but with similar technical background, has already been ready with 800 volts architecture. So their EQS, which gets released in, I think, in April, it's been unveiled, but it's not released yet for consumer to buy. And their equivalent of E-Class, that's coming in, I think, July. So all of those are coming on 800 volts architecture, and their SUVs are still the ones that are already released, which is EQC and all of that will, and their further updates will continue on 400. And that's basically in the entry level SUVs, and that's because they will be cost centric. So the transition there will still be far away. And I think the next slide will try and explain why that's the case, that why entry level vehicles will still be at 400 volts and why the higher, more premium kind of category vehicles will move to 800 volts. But as you can see, car companies like Porsche or Audi are already ready with their offering of 800 volt system across cross car line. So all their vehicles are now optimized, ready with that 100 volt architecture, and that's because they've matured across their different brands, the Volkswagen group. So they've got higher volume. They've been able to push prices very further down. They've been able to develop more and more power electronic component designs quietly but significantly better than competitors, including Tesla. So I think that's the reason why the new ID3 from Volkswagen is actually selling more cars than a Tesla Model 3 now. Right. So now that I've explained, I tried to give some background on what the typical outlook looks like for different OEMs. I'll try and talk about what is the move to 800 volts. And this also will try and explain why some of the OEMs earlier don't yet have 800 volts. So today's switching MOSFETs, which are IGBTs, your basically switch things that switch high voltage, high current across are still IGBT based, silicon IGBT based, and the move to 400 volt silicon carbide, because silicon carbide is still new, is an additional $400 £400 I think cost increase. I just explained earlier, your max profit on a component is about across your vehicle on your componentry is about £100, because you have to address for marketing and warranty and all the spends. So £400 is just not achievable, just not possible for many companies, because they don't have volume, and two, they can't. I mean, the material costs are high. So with companies like Volkswagen, which sell 10 million cars a year, for them it's easy. But smaller companies like Volvo, and if I just flick back, that's why you see Volvo as an interesting element, which I forgot to mention, is sitting on 400 almost up to 2026. And that's primarily because the volume of Volvo is still in the range of 600 to 700,000 cars every year, whereas the likes of Mercedes, that's Daimler or BMW, is between 5 to 2.7 million. Same is with Hyundai. With Volkswagen, they go very high, 10 million, because they've got Porsche, Audi, Lamborghini, all those brands with them. Lucid is a very, very premium brand, so they will sell at higher cost than most of the other architectures. And that's a major driver towards achieving 800, the cost today. But the other element is when we move to 400 volt silicon carbide, you also get about 3 to 4% improvement in efficiency, and that contributes to 3 to 4 kilowatt hours of battery. And each of that contributes to 300 to 400. Now, where does that number come from? It's not just the cells, it's your packaging, it's your manpower, it's your assembly, it's your structure, weight, efficiency, all of that put together. The net impact on the car is 300 pounds. That's basically 100 pounds per kilowatt hour is typically the impact that you have in around 2025. Today, it's even higher. Today, that number is about 180 pounds. But this number also includes the reduction in the cost of cells. And with that, we look at 100 pounds as a typical per kilowatt hour. With every 1 kilowatt hour saved on the battery, meaning every 1 kilowatt hour less we have to spec the battery, we save 100 pounds on the vehicle. And that's a very important number for an OEM. But when we move to 800 volt silicon, which is not available right now, the cost goes even below, because then the current goes down. So the creepage clearances and all other areas around silicon carbide packaging significantly reduced. So that 400 increase now comes down by 600. So we save 200, start saving 200 pounds on a vehicle rather than earlier cost. So as compared, compare number 4 with number 1, we actually start saving 200 pounds per car, but that's still far away. And silicon carbide cost reduction is moving steadily along as the dies become more and more efficient. So the reason why those costs are high is, for example, when, say, if you look at semiconductor manufacturing like Intel, they would have always a number called yield. So typically Intel's yield is 66%, which means, for example, if I have a big wafer of silicon that on which I etch my transistors, I will have 66% of that coming to me as properly etched. What that means is 66% of that I would be able to sell it as a Core i7 is what Intel calls their 100% yield ECUs, processors as. If you burn 50% of your die, it is sold as Core i5. If you burn 75% of it, it is sold as Core i3. And if you burn it completely, when it burns, you still have switching available, but it is sold as a Pentium D processor. So net Intel sells everything, but that doesn't work in OEM world. If you burn it, you burn it. You can't use it, because I think you have to always optimize for a Core i7 kind of performance. So I was giving an analogy. It is not exactly as linearly related between the two. So the right time to move to 800 volt is around 2025, because at that time, all these industrializations will start coming in. And further down the line from 2025 to 2030, why does the number 2030 come in most governments trying to declare? That's when silicon carbide will be mainstream. It will start coming in like series production across different semiconductor manufacturers. Silicon has almost reached its limit now with Apple, which is now leading. Earlier, Apple used to use Intel, but now Apple has led its own architecture, which they followed the ARM architecture, and they've now released their Apple M1X processor, which is sitting on 5 nanometer lithography, and silicon to silicon bond length is 4.29 nanometers. So 5 nanometer is pretty much the practical limit on silicon. With silicon carbide, you can achieve more efficiency because the channel width is high, so you can have more electrons flowing in your channel as compared to silicon. So I'm just trying to give a simpler explanation, although one can spend more time. But moving to, I just had a video that explains about an upcoming platform. See only the battery packs are packaged. There is no battery management system. It's only the cells, and they're part of the structure. your inverters and motors are now integrated as one house in one element. This still has this still shows inverter cleaner, but now we'll see a concept where the machine inverter all is sitting in one axis. It's just sitting vertically integrated rather than horizontal, trying to save space. Because battery is part of the structure, it will just fall down on an impact. And now comes to the part that I've been focusing on. In a minute, charge, more space. Charge at 400 and you charge at 800 using the same component. Right, moving on. So I'm coming to my last section, which is I'm going to take a case study of an integration example. And if you saw in the last part of the video, which talked about charger and a DC-DC, which is supporting 400 volts, 800 volts, feeding back to the grid. And I'm going to explain a little bit on that as a case study. Why is there an interest in going towards an integrated charger, DC-DC, or a BMS as well? So on your left hand side is a typical architecture in which you have your onboard charger DC-DC sitting outside and the battery management sitting inside your battery. As I said earlier, your contactors, your wires, all of that start increasing. Wires, contactors are all passive components for a electronics or a power electronics engineer. They are more of a headache to have on the vehicle because one, being passive, you can't actively detect a fault. The only way to detect is by manually accessing it. And as the architecture start getting more and more compact, more complex, they become difficult to access as well. So trying to eliminate the harness improves cost. Cooling connections become easy if you have just one cooling plate across your components, and having just one microcontroller rather than different microcontrollers. Like for example, today you have a separate microcontroller for a charger, separate microcontroller for a DC-DC, and separate for your battery management system. So all of them have to talk to each other. And in that process, if you and different manufacturers will produce different parts. So there is high chance that one error could lead to another cascade, and that cascade, if it continues, sometimes becomes very difficult to even solve, taking more than like 4 or 5 months to understand the interaction matrix because it's so complicated. And just to explain an example, a battery management system is not designed to open contactors, but it's not designed to always open contactors, but it has authority to open contactors whenever it wants. So if it loses power, or let's say if there is a crash and it detects it, it will just open the contactors. Usually the contactors are accessed by a vehicle supervisory control. But now, if there is a fault on a DC-DC and battery management sees that as a battery fault, which may not be the case, it will just open the contactors and it will not close it. That will not be fixed until you go and access the vehicle. And because the fault in the DC-DC would be passive linked to the wiring harness, let's say, for example, you will never be able to figure it out what happened until you access the vehicle and you saw actually damage on the vehicle. So that's one reason why we're trying to move. Second is cost. If we can try and have just one control board, you almost save about $20 to $22 per part, because control boards, you save the PCB, you save real estate, and you'll have to spend slightly more money on your microcontroller, but it will be definitely less than having 3 microcontrollers. So what we will talk about is today, present day, the efficiencies sit around 93% for a DC-DC standard operation at peak, and about 96% for an onboard charger. And at low load, a DC-DC typically is at about 74 to 80%. And that's primarily due to non-planar magnetics. With planar magnetics, more integration, less wires, you can have low load efficiencies of 93 to 94%, and your peak efficiencies could go to 98%. And we'll go through that. The most important aspect of this slide that I want to focus on is the volume and mass. So as you can see in the 2 yellow lines on the right hand side in volume, with an integrated approach, you have about 7 liters of packaging space that you can package all of these in. This includes a 22 kilowatt as well. Whereas with an 11 kilowatt and with all those components, it do the same function sitting separately, you have almost thrice the volume, which is about 19 liters of space. So even on the weight, you have almost twice. And as it goes, weight affects efficiency weight, because the lesser weight you carry on the car, more you save for the battery to push your vehicle forward. So all of that contributes to cost significantly. And that's one reason why this integration, you would now start seeing all OEMs starting to present why they are the best in their integration and why they are the best in their charging system. For example, Lucid's the latest one, saying they call it as the Wonder Box. And now Hyundai just calls them as ICCU, and they spend significant amount of time towards the end of the video so that customers can remember that about the improvements that they have with charging vehicle to grid offerings. This is just trying to explain the earlier slide in slightly more pictorial form. So earlier you would have your components sitting different and them all coming together. Now you at least have your onboard charger DC-DC coming together. The battery management system is still sitting as part of your battery. Going forward, you would have around 2025 your onboard charger DC-DC actually part of your battery pack. So the way it would be that a battery assembler for an OEM would just assemble the battery modules into the pack and leave a serviceable hatch where the onboard charger DC-DC and a BMS will come and sit in. And the inverter and the motor will all be integrated in just one element. So at the end of you just would have 2 components: is your drive unit and your battery pack, which will have your charging. Just as simple, very clear, and you just have one DC cable between your HV battery and your inverter, and that's it. No more set of AC cables going around, no crimping issues at all. And therefore that will give more offerings to the consumer. This is a typical block diagram of what I was talking about. So your onboard charger, your DC-DC converter, your BMS and master control across your onboard charger and your DC-DC will all be integrated inside of one box. That would include your contactors as well. But I think the master controller will also define how the contactors align and realign to change the configuration of the battery. So the bus bars on the battery will change as the contactors change their alignment inside this box from 800 to 400 volts. So this talks about AC charging use case, your DC charging use case into the contactors, AC charging directly into the onboard charger, converting AC to DC and going into the battery. your consumers still being fed power through the contactors. And with an integrated approach, you could actually use the battery's cooling system, and this saves money because you don't have to design a separate cooling system. So you can actually have just two inlets coming from the battery itself, which takes the battery cooling fluid into this component, cools it, and then gets recycled across your compressor in just one recycling system. So you save money on your coolant channels as well. And all of these small things seem small, but actually they add a lot of value and cost. The mechanical aspect of it adds a lot of cost saving on the car. And most importantly, your vehicle network as well. Now, as a 12-volt architecture, you are now talking only to one controller on your high voltage side, apart from your inverter, which is your the microcontroller, which has your BMS as well. You're not talking to an onboard charger. You're not talking to a DC-DC and a BMS separately. You're talking to just one brain, which is telling what's happening on a charging scenario. So if the vehicle is not moving, it just makes it so simple. And why it's important is every time an ECU is listening to network, for example, CAN, it is awake, which means it is in a higher power draw category, which takes the power off your 12-volt battery. So why this integration is also helpful is you would have less number of ECUs awake and therefore drawing less power from your 12-volt battery. And that these are some of the smaller hidden benefits of all of these architectures that are adding value. Because I think what's not yet understood in the market, people see the big HV battery, but they neglect the small LV battery, which is still a lead acid. And lead acid battery only goes up to 500 cycles. It cannot be discharged below 50% SOC, else you have to throw it off. So improving the efficiency on that architecture is also important. And all of these integration approaches have to take all of that in mind and are also trying to see how we can improve that. Because I think what one has to remember also is in an IC engine, when you're running the engine or you're fueled up your car, you have an engine to power up your battery, but every time you are sitting with a HV battery and you're charging your LV battery, that's a 12-volt lead acid, you're cycling your battery more, and in an IC engine, you actually have your alternator, which is powering your 12-volt bus. But with more and more integration and people trying to delete the BISG of the integrated starter generator of the battery electric, now the HV battery and the DC-DC have to do the function of topping up your 12-volt battery. So actually, you would end up in cycling your HV battery and your LV battery more. And cycling the LV battery is actually lead acid battery is actually going to take it to its lifetime usage faster than what you would see in a typical ICE, like petrol or a diesel car use case. So just to explain again in another format, the HV battery will for 2025 will be having both 400 and 800 volt configuration on it. So the contactors will align and realign to meet that target. If you give an 800 volt DC gun input, it will align to 800 volt and take the charge in. But if the consumers are still 400 volts, like for example, inverter or HVAC, there would be a high voltage DC to DC conversion trying to convert from 800 to 400. And I think that's why the switching has to be more and more efficient as we move forward. So this diagram is just to try and explain what I meant by a master control board. So it doesn't mean that there will be no logic in these components. The onboard charger and DC-DC would still have. Those will be more of logic device based, for example, like FPGA based, rather than a full-fledged microcontroller. They will still get a command from the microcontroller. The main processing will happen in the microcontroller. For example, the battery modules may just have the balancing ICs and a small logic device, which gets told by the microcontroller sitting on the main control board. I think you are above your voltage start discharge, and it will start discharge, the passive balancing approach, and then it will stop when it gets told to stop. Similarly, another thing that is important to probably explain is in order to improve efficiency from what we saw 80% to 93% earlier, these different onboard charger and DC-DC topologies will start getting converted into phases. What I mean by phases is rather than just have a big transformer coil and a big step down, step up phase, one would have multiple layers, each layer doing small elements of it. So for example, nowadays a standard is 4-phase DC-DC. So each phase is doing 1/4 of your conversion. That all adds up, and that's basically done to reduce your losses in switching on your MOSFETs. Primarily, that's the reason. So for one would have each phase would have a logic device which gets micro to do what it wants to do. The other benefit of that is you can start designing your power electronics in such a way that half of your phases would be active for a 400 volt, and for an 800 volt you would activate all of them. So this is just trying to innovate with what you have, is what one can say. So with 3.6 kilowatt, if I just had one phase of it, I would have, let's say, one AC charging, one AC to DC charging, and I'm giving 3.6 kilowatt to the 12 volt bus in a standby. The other phases will be off, so I will be saving power there. In a full usage, I would be activating all of them for a charge and reducing it down to 12 and 14 volts in whichever way it is required as per the demand. So it is power on demand rather than always on. And that's an important statement. Power on demand is basically, as the demand grows, we will give more power. Whereas today, we just keep it on all the time and we just use less power. And that's why this efficiency of 80% here start going to 93%, because we'll just switch off those devices which don't need to be on. We'll just keep maybe just one phase active for a low load condition. I think these are some of the new things that are coming across electrical architectures. Moving forward, I just wanted to give a roadmap. I just wanted to give a map of where the different power electronic suppliers are. So what one can see from here is pretty much everywhere in every country where electrification has been taken off heavily, you see more and more tier ones coming up, and as well as the tier twos coming up with all these architectural supports. So be it Switzerland, which has always been at the forefront, to all the way to something like Innovance or Delta in China, which are also coming up, and almost one can also look at players in Germany like Bosch, who have been very conventional approach driven, or Kostal, who have been also very conventional, also picking up these things. So almost across the landscape, between advanced development to high volume to conventional, everybody is now getting ready on these four fronts. So it's not something that's I think happening in one or two small clusters. It's happening across the board. So I think what I was trying to explain earlier was you would have multiple phases, and in order to try and explain that a bit more, with planar magnetics, you would have your magnetics mounted on your PCB rather than your coils and chokes sitting separately, or your transformer coils sitting outside your PCB. Right now, you will have them mounted on your PCB, and they will be assembled as part of your pick and place process. And planar magnetics actually help you to achieve higher frequency for switching, and they're optimized for reducing their magnetic losses actually. So the silicon carbide, again, not available yet, but when it becomes available, will obviously give more improvement, and that's when you need that high efficiency. So what we see on the right hand side is if you see in the left part of the figure on the graph, the blue shaded region, that's where the phase approach helps. You can increase the number of phases as per demand, but when you don't need the phases, you can just turn them off. Therefore, you will always be almost at full load for that phase, therefore giving high efficiency. a problem with DC-DCs are if when you go on low load condition, your efficiency drops down. Similarly, with onboard charger, your power factor correction, again, transformers, planar magnetics will get mounted on your PCBs. It will save more space. And I think with silicon carbide, it will also help improving its efficiency further. So these are some of the things, and I think with chargers with higher efficiency, you will be able to offer bi-directional topology. So that will help in vehicle to grid offering on the vehicle. Then I'm coming to the last couple of slides where I'm trying to talk about silicon carbide. So silicon carbide is not fully ready yet, but the primary reason for silicon carbide is the die sizes are very small today. So they're 1/4 the size of a typical silicon wafer that goes into production, and that really affects the cost, and that's getting improved. And as it gets improved, one would be able to start seeing more and more adaptability of silicon carbide with reduced cost. The other thing is that the junction temperature of silicon carbide is much higher, so it can sustain, it will be more efficient across higher operational area on a time versus performance graph. And I think other than that, it's more of talking about how the production scales up really. So ROHM is one of the leaders in silicon carbide. With their estimates, they've already started lining up their assembly lines for 2022. As an example, ST is coming heavily. So Tesla Model 3 was the first car which had silicon carbide MOSFETs. Not everybody knows that. So ST Gap was custom designed for a Tesla Model 3 by ST Microelectronics, and they are right now also leading the silicon carbide. And Tesla has been actually driving that, to be honest, the adaptability of silicon carbide. And if you get a chance, try and have a look at Tesla's silicon carbide MOSFET approach to the inverters. It has been quite ahead of the curve, at least 10 years ahead of the curve at the time Model 3 came in. So as I said earlier, ST, ROHM are clearly some of the I think leaders in this. The Infineon Cree are still falling behind, but I think the other area that on silicon carbide I forgot to mention is silicon carbide also handles better transient voltage use cases. What I mean by that is silicon is slightly slower to handle dV by dt losses, dV by dt, I think energy flow through the controller. It takes time for it to detect that, see that, whereas silicon carbide is almost fast. That is why it will be a very big boon to all automotive companies, because today when we have a transient voltage coming, transient voltage is, for example, if you lose suddenly a contactor under load, that energy has to go somewhere. It typically travels through your component, and your MOSFET is slow to detect it. In result, it will burn your capacitors out, or it will cause a fire incident in the car. With silicon carbide, we will be able to see that transient spike, and therefore try and kill the spike through an active clamp or an active short to the body of the component, to try and therefore save the capacitance from being lost on the vehicle due to a burn event. So that's basically trying to give some input on silicon carbide, and with that I come to the end of my discussion.
So participants, do you have any questions? Participants? So shall I ask one question, sir?
Yes, ma'am.
Sir, in most of the EVs we are going to use all the power electronic components. So will be there any risk assessment calculation will be there in that?
Yes, so as I said earlier, I think every component has to have lot of risk assessment going around it. I just tried to talk about transient separation earlier. The other is harmonics, which is oscillating voltage on your HV bus, and you need to have all those protection strategies built in your power electronic design, which is for a transient separation, you will need to have your TVS diodes spec to the right uh, voltage spike that comes in your bus, or for your harmonics, you need to have the right amount of X or Y capacitance. The other element of that is if you have wrong X capacitance designed on your component, it will actually feed a spike back onto your battery. So that will take the fuse out on your battery as well. So all of that has to be taken into consideration when you design a component. So it no longer will be what has been happening until 5 years before on our electronic on HV side, which is most of the time things used to get assembled on a rig and then tested. It will now be start being done more in advance. So at a design phase, you'll have to start putting together different topologies and start understanding if a spike comes, how the different components look at it. So yes, this will be a very important work stream going forward. I think there'll be more and more focus being given on what nowadays is being called a system, HV, high voltage system engineering. So that will be addressed towards this aspect of protection.
Sir, there is one more question in the chat box. It's from Mamta Patwardhan.
Right, why 800 volts? Can we go more voltage? Yes, 800 volts is because that's where the infrastructure can reach today. 1200 volts is what some of these small performance companies are trying to aim for, but the infrastructure doesn't support it. Today, 800 volt is the max the infrastructure can support. And the way we have to always try and imagine this is when we try to increase the voltage class, everything in the internal cascade has to start scaling up. And it's almost like when, let's say, the prime minister wants the nation to go on lockdown, it has to go to the state, then to the district, and then to the villages. So everybody has to take time. So the semiconductor companies also have to get ready to switch at that frequency and that voltage class. So not everybody is ready, is one. Very few are ready. So the problem with that is every time it comes to, with automotive, the biggest problem is cost. So higher the volume, lesser the cost, more people adopting it, more reliability, people will start adopting it. If it's if it's in aerospace, it's not about cost, it's about weight. That's the big difference between the two. Automotive is clearly directed around cost, with an with a with a aerospace. You would, if I were to offer 1200 volt with, let's say, one supplier which is 500 pounds more costly, but it saves me half a gram, the aerospace company will jump over it because they're running for grams. Because every time they pick a gram up, they save energy. This They pick less of a gram up, they save energy. Whereas with railways, that's where you see even higher voltages in kilovolts, right? That's because with railways, you no longer have problems of packaging. You no longer have problems with cost because you're carrying more people in one wagon. It's a one-time investment, and you no longer have problems with weight. So as we see in rail, you already have 10 kilovolts applications as well. So just to answer the question, that's the reason why 800. It's because you have to take everybody along with you all the way from your tier 3 and tier 4, and that takes time.
So thank you, sir. One more question is below that only. From battery health point of view, which voltage level is better?
So, uh, from a battery perspective, battery is agnostic. The reason for that is your voltage class is merely a series or parallel combination of your configuration. For a cell who's sitting, it just sees 3.2 or 3.6 volt based on its chemistry. How you connect all the cells in series determines what your end voltage is. So what affects the battery is your current draw. So for example, if you just Ohm's law, you have less voltage but more current coming out of the battery, which means each cell will be pumping more current out. That will cycle the cell faster. So that's actually worse for a battery. Whereas if you're slightly on higher voltage, you'll be giving out less current, so you will be actually saving more of cycling of the I think all these terms sound very complex. They are very, very simple. So always the way we have to imagine that is, in a battery it's nothing, it's just a cathode and anode, and there is a separator and electrons are moving. Every time you move the electron forward and backward, you leave some behind. So the number of times you do that is limited. And when you move, that is basically current is moving, and the higher the voltage, less the current. So the less current you move, the more of battery you save. So higher the voltage, less the current, you save battery. But if you increase voltage and if you increase performance, it's you have no benefit then, because then you're still cycling at the same rate.
So participants, do you have still any questions? Sir has also displayed the mail ID. So if you have any queries, you can just contact him on the Gmail account. So if you have any questions, you can just unmute yourself and you can ask the questions. Otherwise, drop your question in the chat box. So shall we conclude, sir, now?
Okay, thank you very much for inviting me. Thank you, thanks a lot everyone.
So to conclude about the session, actually it was a very nice and informative session. Sir has discussed many points, but I will just try to conclude in a precise manner. So, starting with the charging system requirements, like discussing about the customer point of view of purchasing cost, driving range, and difficulty of charging. He also discussed about how the charging system improvement can be achieved through to change to the higher voltage of 800 volts. His detailed review on 2019 400 volt BEV platform, and now how the integrated components with high power density and battery pack structure have been adopted will be adopted into a 2021 800 volt BEV platform. He also made us to imagine how a powertrain of BEV will look like in 2025. It was a very excellent presentation with a nice video representing deep insight of the architecture of a car with a battery and all other components of EV car. His comprehensive talk on a case study of integrated onboard chargers, DC-DC, and BMS charging. He also focused which are the suppliers who are leading in power electronics for EV. So thank you, sir, for your such an informative talk. So on behalf of Department of Electrical Engineering, Modern College of Engineering, I thank Mr. Chinmay Joshi, sir. In spite of his busy schedule, he spared his time. So thank you very much, sir. So now I hand over the next session to the coordinator of FDP, Dr. Mrs. Rushali Khatawkar.
Thank you ma'am, thank you Dr. Khatawkar, thank you very much.
Thank you.
Thanks a lot, Chinmay Joshi, for
Yes,
excellent presentation. Very much detailed explanation you gave. Also, you have shown one video, so we could imagine how the EV battery management would be and its architecture would be. Thanks a lot once again.
thank you very much. Have a good day everyone, and a good week. Bye.
Now we'll start the valedictory function soon. Honorable Principal and Convener of this FDP, Professor Dr. Mrs. K.R. Joshi, respected Vice Principal and HOD Co-Convener of this FDP, Professor Dr. Mrs. N.R. Kulkarni, all participants and my colleagues. A very good afternoon and warm welcome to one and all for this valedictory function for AICTE funded 2 weeks faculty development program titled Electric Vehicle Applications, Control and Smart Charging Using Artificial Intelligence, Series 1, Electric Vehicle Design, Applications and Control Strategies. These FDP sessions were delivered by the distinguished speakers within India and out of India. Am I audible to all of you?
Yes, ma'am.
The all speakers covered the various topics like overview of e-mobility in India, smart battery management and charging, motor design and control strategies with controllers for EV, protection features, faults tolerant capability, V2G and G2V, selection of drives and batteries, then charging infrastructure, use of software for design and control of motors for EV, materials and architecture for EV, and impact of electric vehicle on grid. I'm pretty sure that the FDP has given an enriched experience to all participants about the knowledge gain and deep insight of the upcoming field electric vehicle. Now, I would like to request the participants to give the feedback on this 2 weeks FDP. I would request Professor Anil Revankar for his views. Revankar sir?
Yeah. Can you hear me?
Yes sir, you are audible.
Yes. I'm honored and humbled that my colleague have asked me to speak today. I would like to thank Dr. Kulkarni, Dr. Joshi, and team of Dr. Rushali Khatawkar, Rishikesh Shirke, and Madhura Tuljapurkar for successfully conducting the FDP on the topic of electrical vehicle design, its application, and control strategies. The lectures by eminent personalities were treat to hear, and I have personally learned a lot from their work, their experience, and their knowledge. I really thank you. Thank you again.
Thank you, sir. Next participant, Dr. Arvind Chain from MGM College, Aurangabad.
Thank you, madam. Good afternoon to all. Myself, Dr. Arvind Chain. I'm the coordinator of Electric Vehicle Laboratory and the associate professor at MGM University, Aurangabad, Maharashtra. I would like to say that this FDP of 2 weeks was very extensive, and I have seen there are speakers from all over the world, and there was excellent and detailed presentation by each speaker, and giving us the learning for application, learning for research and development. So I thank all the speakers for delivering excellent lectures, and I thank especially the organizers, Madam Rushali Khatawkar, Tuljapurkar Madam, Mugdha Madam, for organizing this excellent FDP. And I would like to invite all the interested faculty members, researchers, and industry experts to MGM University Aurangabad campus, especially to the Innovation Incubation and Research Center, especially to the Electric Vehicle Laboratory. Thank you all. Thank you.
Thank you, sir, for inviting all those who are interested. Next participant, Dr. Deepak Bankar, HOD Electrical Department from Bharati Vidyapit. Sir, you are not audible.
Hello, am I audible?
Yes, sir.
Good afternoon, all. Myself Deepak Bankar, Professor and Head of Electrical Department from Bharati Vidyapit, deemed to be University College of Engineering, Pune. So I would like to appreciate the efforts made by the organizing committee of Modern College of Engineering for organizing the 2 weeks FDP on electric vehicle design, its applications and control strategies. It was really a knowledgeable FDP, and organizers have taken care of covering all the aspects related to the electric vehicle, right from motor selection, battery management system, its modeling, and also the various issues of impact of EV on electrical grid and its reliability. Also, the focus of EV policies was discussed in the FDP. The resource persons from India and abroad had really explored their knowledge in simpler way. Actually, few candidates from our university are also doing PhD on areas related to the electric vehicle, like switch reluctance motor, its design and analysis, DC-DC converter, BMS with supercapacitors, fast chargers. So we have also developed an electric vehicle laboratory in association with the industry. So we found this FDP as an excellent resource material for us, as well as my research candidates. So overall, it was very much fruitful and knowledgeable event, I can say. So once again, I would like to thank organizing team, especially Kataukar madam, for arranging such a nice FDP and coordinating more than 25 participants, more than 25 speakers, eminent speakers from India and abroad. Thank you, ma'am, for giving us opportunity to attend such a nice FDP.
Thank you very much, sir, for nice words. The next participant is Dr. Mamata Patwardhan from Rahuri Krishi Vidyapit.
Hello, may I audible, madam?
Yes, you are
So
audible,
first
madam.
of all, first of all, I want to thank all organizing team for the successful FDP conduction. I also thank for selecting me as a participant. So recently, our Honorable Road and Transport Minister highlighted the importance of electric vehicle, and on the background of climate change, this electric vehicle is a burning topic for us. So this FDP will surely highlight these all aspects, and that will give the training to our engineering mind in this trust area. So this knowledge is very much useful for development of basically the new curriculum, students projects also. All speakers as well as topics were very excellent, and all aspects of a very huge, large thrust area of the electric vehicle theme was well elaborated. So this FDP's all activities were nicely planned and punctual. Every communication was also carried out in proper manner. So I think this total FDP was a wonderful experience. Thanks to Kataukar madam and team. Thank you all.
Thanks a lot, madam. Next participant is Dr. Sunil Gaikwad.
Am I audible, madam?
Yes, sir.
Thank you, madam. Dear all, good evening. Respected HOD Kulkarni, madam, Dr. Khatakar, madam, from Electrical Department of Modern College of Engineering and Management. I heartily congratulate to team for successful conduction of AICT sponsored 2-week online FDP on electric vehicle application control and smart charging using artificial intelligence from 1st to 14th December 2020. It was a long span of 2 weeks. But during these 2 weeks, we enjoyed a lot because around about 40 plus hours sessions were carried out. And experts were from the different domain, from different areas, like from the government organizations, from industry, from India, from abroad India, from different research institutes and sort of the things. The moreover, they focused on the different research areas where our research aspirant can more focus on, and we being a guide or the student in the same domain which we have already updated a lot. The lot of aspects were touched. It was from electrical domain, from mechanical domain, from electronics domain, and from lot of information was forwarded under one roof. I always said to each speaker that we never used to get such good information in a single book or in a single website. We were also updated for the different funding agencies and different live projects what these experts are working on. As well as it must have taken a lot and great pain to the coordinators for working from the day one when they started thinking about this FDP to start. There lot of brainstorming must have happened to whom to select, whether he will be given a right time, right day, and whether the online session will be happening properly or not. Because this online session is a great challenge for these FDPs and STTPs. So we all were fortunate to be the part of this technical fair, and I congratulate again to all experts as well as the FDP coordinators wholeheartedly from PVG College of Engineering and Technology. Thank you, madam, very much.
Thanks a lot, sir. Next participant is Mayuresh Bhusekar from Industry, Force Motors.
Hello, ma'am. Hello, everyone. I am Mayur. I am from Force Motors Limited. First of all, I would like to thanks to Khataukar madam and all other organizing members, and of course, I would like to thanks to our speakers for giving their time. Currently, I am working on commercial vehicles, design and development of electrical and electronics components. So it was a nice opportunity for me to explore EV related things, and my core experience is into wiring harness development. So it was indeed very informative and knowledgeable program for me. And I feel the main crunch of the program was complete EV industry analysis, basically. Right from EV components to in-depth various design aspects was covered, like types of control and types of motors, grid system, etc. So great learning for me being an automotive industry person. And agenda of the program was excellent. Just I would like to add one more point. Hello, am I audible, ma'am?
Yes, you are audible.
At the end, I just would like to add one more point that if apart from all the topics, if we can add a topic related to homologation, that is, if EMI EMC related challenges are there, if any, and apart from that, if I'm basically from wiring harness design and development background, so if we add those points related to wiring harness challenges and development, so it will be very much helpful for people like me from industry. And so overall it was a great learning for me, and it was a rich experience for me. So thanks, and that's it from my side.
Yes, thank you very much for your frank feedback. If the opportunity is there, we'll definitely think of the suggestion, whatever you have given.
Okay, ma'am.
Thank you all participants for giving the feedback. Now, may I request our HOD, our Vice Principal, HOD and co-convener of this faculty development program, Professor Dr. Mrs. N.R. Kulkarni Madam, to share her views on this.
Okay. Thank you, madam. Good evening, one and all. First of all, I want to congratulate all participants for completing 2 weeks FDP on electric vehicle application, control and smart charging using artificial intelligence. We got sanction for AICT FDP for 2 week AICT FDP, but due to pandemic situation, we have to switch over to this now series, and this was first series. Today we have completed first series. Electric vehicle design, its application and control strategy. It was really feast, I can say that technical feast to all of you, because all over the world I can say that here speaker have given excellent knowledge to all of us. We know that here electric vehicle is now current very hot topics for all electrical engineering. In that is the, I think that in 10 years back, we have more focused on renewable energy. But now that is we are focusing on smart city and electric vehicle. So here that is different sessions were conducted, and next series also we are going to conduct on the intelligent control for that is the electric vehicles and other application. I welcome again you for the next series also. You can enroll for that one. That series will start from 18th of January and it is again 2 weeks FDP. We have actually invited again that is the eminent persons from all over the world and also NIT and IIT. So thank you for your cooperation. Most of that is participant attended, above that is the 80% attendance is there. After all, I am teacher, I count attendance also. So here that is the most of the participants have attended the sessions and they were very enthusiastic to ask questions also. So I thank all of the participants. Also, I thank to our principal, Dr. Kalyani Joshi Madam, our chairman, Progressive Education Society chairman, Dr. G.R. Egbote sir, our secretary, Professor Shamkant Deshmukh, our college development committee chairman, Professor Josna Egbote Madam. Always they encourage us to conduct such programs. Before this also, we have conducted 3 days workshop on electric vehicle for our third year and last year student. And that was also very nicely conducted and that is the huge response was there for that workshop. So again, I will be eagerly waiting all of you for the next series also. Thanks for attending and completing your this first series. Also, I thank to all my that is colleagues, Dr. Rushali Khatavkar, then Professor Sharmila Chaugule, Professor Madhura Tulzapurkar, Professor Rushikesh Shirke, Mugdha Bhajekar Madam, Professor Mugdha Bhajekar, Professor Shilpa Joshi, and Professor Borkar, Professor Shreyas Ketskar, who are directly involved in this workshop. Indirectly, all my department staff have been involved and they have that is the participated in the sessions also. Thank you once again. Over to Khatavkar Madam.
Thank you, madam, for your views. Now, on behalf of Modern College of Engineering, Electrical Engineering Department, I'm very much grateful to AICT for sponsoring this FDP. I'm extremely thankful to Chairman P Society, Dr. G.R. Egbote, for giving the permission to conduct such a wonderful FDP. Also, I am thankful to our Secretary, Shamkant Deshmukh sir, Josna Egbote madam, for giving the required support for this FDP. I am very much thankful to convener Dr. K.R. Joshi madam for strong and consistent support. I'm also thankful to co-convener Dr. N.R. Kulkarni Madam for all-time support and guidance. I'm grateful to all distinguished speakers for their huge and heartfelt contribution to raise the heights of this FDP. I am very much thankful to all participants without whom this FDP would not be a grand success. My indeed thanks to our coordination team for the efforts they put in right from search of resource person till the smooth conduction of the FDP. Also thankful to the registration, attendance and feedback team, finance and documentation team, without whom the smooth conduction of this FDP could not be possible. Once again, thank you all, and I declare that this FDP valedictory function is now over. Thank you all.
Thank you, madam.
Thank you, ma'am.